synchronize that?
Yeah.
Did it drop down any names, or is everything still red on the left?
It dropped on one name.
I don't know what's going on with it. Anyways, I got rosters for everybody, but this iClicker software is a pain in the you-know-what sometimes. All right. Right, whoa, it's 9:08. Let's get going. Couple comments for you just about exam 3 coming up Thursday. Today's lecture is you're going to have in today's lecture, you're going to have the important thing for exam 4. All right? And so let's talk about exam 4 next Tuesday for just a minute. And we'll talk about it again on Thursday. And hopefully nobody will mess up and skip exam 4 because so there's a spec from the amended syllabus, 50-point exam, November 14th, that's next Tuesday. Remember that if you missed either exam X or exam 3, you absolutely, positively, without any doubts, no drips, no runs, no errors, you got to be there for exam 4 because our maneuver for grading combined with absences on exams is the maneuver where we drop the lowest score and we keep the best 2. But if you're only there for 2, we drop the one that you missed. All right? But if you have 3, then you've got probably a couple good ones maybe. And we'll keep those 2 good ones and drop the lowest one. All right? So that does not work if you're absent, whether it's excused or unexcused. That's how we deal with it. That's the one that gets dropped. And by the way, if you have exam scores for exam X and exam 3, and you like those scores, and you think to yourself, I'll just skip exam 4. Keep in mind, exam 3 was easier than exam X, and exam 4 is probably going to be a little bit easier yet. So do not be overconfident, because when you're overconfident, you get caught napping. And you do not, I'm not looking at anybody, but you do not want to be caught napping, especially on the final. Now let's talk about the final for just a second. Yeah, final exam, really nice. 7 a.m. Sorry, nothing I can do about it. If you want to complain, go complain to the provost or President Hitt or somebody, some of the big shots, because, it seems to be customary, a tradition here at UCF. Oh my goodness, I have never seen another university with 7 a.m. finals. But that's what we got. So start planning to be here at 6:54. Good, great. And you freshmen, you newbie freshmen, let me just clue you in. I'm not going to be nice if you're late. There's no Mr. Nice Guy. I mean, you just got to be here. So telling me that the dog ate your alarm clock or anything like that, it ain't going to cut it. You just got to be there. And it's 7 a.m. Your 1 o'clock p.m. finals, those are a little bit nicer. But this one, you just got to do it. You can't let yourself down. You just got to get it. And for those of you that are newbie freshmen and are not listening, I'll just say it now. It'll be permanently recorded on the YouTube, and I'll be able to tell you later, you didn't listen. So listen now. If you're a freshman and you've never been through exam week, what you don't want to do is overstress yourself, because then you're going to come down with some, especially at the end of fall semester, you're going to come down with some nasty cold or something like that. Sleep is a weapon. Do not stay up all night. Listen to your mother-in-law. I'm going to nag you guys like a mother-in-law from another planet. Do not stay up all night studying. Do not do it. You're going to get yourself sick, and even if you're not sick, you're going to show up to the final, whatever final it is, whether it's my 7 a.m. final or any other final, and your brain is going to be like at 50% efficiency. Now, if you say to yourself, yeah, but I can ace it even at 50%, yeah, don't try that in my class. You won't ace jack. Maybe you'll pass. So treat it seriously. Make sure you eat. Make sure you, I'm starting to sound like your mother and your ma. Eat, sleep, get rest, work out a little bit. Do not just totally bear down and study. You may say to yourself, I can do it. Yeah, but maybe 1 or 2 of you can do that, but the rest of you are going to come down with something really nasty, or you're going to sleep through your alarm, and the dog ate your alarm, and then you're going to see me saying, oh no, you have to be here. No dogs eating alarms today. You just got to be. So don't do that. All right, just be ready for that. And for you guys, the 7 a.m. effect, God bless you. And I'm in it too. I got to get it done as well. Now, I want to go and start talking about the brightness of stars. That's our main topic for today. And what I want to do is review a graphic from homework 9 that I asked you to look at and so forth. And we're going to do some clicking. But before we do that, I want to give you a little bit more instructions about the lower half of this diagram. I think everybody's got the Roy G. Biv idea figured out. And this diagram I set up for you, I spent an hour putting this diagram together so the colors would all be righteous. The U and the I are different shades of gray. So let's talk about this whole idea of passband filters, the UBVRI photometric system. Here's a graphic that shows you the transmittance of the various filters. Now, this is from the Andover Corporation up in New Hampshire. And I want you to make a sketch and make it a good big one, because we're going to add some notations to it. All right, now the vertical scale is a percentage transmittance. So that goes from 0 to 100. All right. And on the vertical scale, and the horizontal scale is just wavelength, so you can see that for yourselves. The vertical scale is transmittance. So where those curves are higher, that means at that wavelength, you're getting a lot of light through. And where it dips down to a lower level, you're getting less light there. You don't see those colors, those wavelengths. All right? Now try to draw the vertical and the horizontal axis. And if you look at it carefully, you'll see a curve for the U filter. That shows you the wavelength and the transmittance level where most of the U filter catches light. All right? It's down there in the 300s. All right? And then there's the B filter. All right? And it's a little bit more efficient. The top of the B filter curve's a little bit higher, so try to sketch it in. And then the V filter, that's the highest of all of them. No, I guess the I filter's a little higher. And between the V and the I is the R filter. And this is the filter system that many astronomers use. The horizontal scale's the wavelength. So start it down here at 300 and go up to 1200. And here's Here's 400 and 700. So 400, see those dark lines? A dark blue line and a good dark red line. And those are for 400 and 700 nanometers. So that's your visible, that's your Roy G. Biv in there. And you can see that these different curves, and here's 500 and 600, a green line and an orange line, just for reference. And you can see that the V filter, it pretty much peaks at about 500. The B filter is somewhere between 400 and 500. The R filter is actually at about 600. All right, so, and then nothing is peaked at 700. But then out in the infrared here to the right, you've got, a big, so what that means is you've got a filter that filters out almost all of visible light, but it transmits infrared. Guess what they make infrared optics, lenses and stuff that work for infrared. You know what they make it out of? Silicon. You can't see through it with visible light, but you can use silicon, like the silicon that's in your electronics and stuff. You grind it to a fine lens shape, and you can focus infrared light with silicon. So it's probably this filter, the eye filter, is made from silicon. All right, so we're going to look at this diagram again. I want to show you what the filters actually look like. Okay, so an astronomer is going to buy a bunch of these and put them on the front end of his telescope, or maybe the back end if he's just eyeballing stuff. And then measure the brightness through these specific filters. So if you're only interested in ultraviolet, you put the U filter on and you just measure whatever you see. If you're only if you're only interested in infrared, so for instance, infrared, let's go ahead and make a note. Infrared is really good for seeing stuff toward the center of our galaxy because all the dust and gas, you're looking straight into the middle of it. So to see anything in the center of the galaxy or directly across from the center on the other side of the galaxy, you got to see through a lot of dust and gas. And visible doesn't cut it, but infrared apparently is fairly good. So if you want to see stuff toward the center of the galaxy, it's going to be pretty dim, but definitely use an infrared filter, an eye filter. All right, and so let's take a look at it again. Go ahead and improve your sketches. Here's a blow-up of it. Just go ahead and double-check. And here are the 400 and the 700 nanometer lines. And we're going to do a clicker question here in a minute. All right, so have your clicker out. And I'm going to ask you some basic questions about these filters and some tougher questions. So we're going to go up in difficulty. All right. So, but let me pause for questions here. Yes. Yeah. Yeah, so if you want to only see red stuff and orangey stuff, use the R filter. So you could put it up to your eye if you wanted to. And if you these are highly precise and ultra calibrated tools. But if you see, you go to the dollar store and you see like glasses that are red, like red glasses or green, that's the same thing. It just permits red light to go through. It's just really cheap plastic. So an astronomer wouldn't want to use it. You know what else? Those 3D glasses that you use at the theater, I think one of them is red and one of them is blues. Isn't that how they work? Different colors? And those are really cheap. So an astronomer would use those blue and red pieces of plastic, but for handing out at a theater, and getting scared and stuff. With 3D photos, yeah, you can do that. Another question. Okay, so you guys are all geniuses about this. All right, good. Because I'm going to make you think. And remember, thinking is the way to ace my exams, especially the final exam. And if you don't obey my admonitions for finals week, you freshmen, you're not going to be thinking that quickly or that well. So, question number 1. Go ahead and start it. Multiple choice. Read carefully and think. UV meaning ultraviolet. Hurry up, we're clicking. Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and most of you got it right. Yeah, the U filter. And here's the way, if you got that wrong, a bunch of you did, about 90 of you got it wrong. You didn't vote for A. The way that you want to interpret that is ultraviolet is over here, 300 to 4, and actually below 300 as well. The filter that has the biggest peak over there, that has the biggest transmittance, and that means it transmits the most light in that range, is the U filter. All right, so that's how you want to think about that. Now, here's another way to look at it. This is really what we're trying to, this is why we use filters. We're trying to understand which curve we're talking about. And look at the 6,000 and the 5,000. The 6,000 is brightest in the green. And the 5,000 is brightest in the red. All right? Now, if you look at it through different filters, go ahead and make a note. This is figure 3 from section 5.2. If you look at it in different filters, they're going to have different appearances. They're going to have different brightnesses. You know, it might look dim in one filter and bright in another. Now, let's take another crack at this one. All right, this filter is least useful for observing stars with lots of UV. Go ahead and vote. This is multiple choice. And we're going to do a calculation toward the end of class, so be alert. Have your calculators ready. "20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. The eye filter. The way these things, look at the green one. Look at B. The B filter dips down, and then look right here where my cursor is. About 560, the B filter goes up a little bit. Not much, but you got a little dip, a little upward dip there. Right? That means you're getting a little transmittance in that little, about 560 nanometers. But in general, the further you are to the left or the right, the less transmittance you're going to get. You're going to get a central peak of some shape. Now, the eye filter's got a kind of a weird shape, and that's because it's made of different materials like silicon or something like that. But basically, the further to the left or the further to the right, the less transmittance you're going to have. All right, in general. Now, third question. And I'm shooting to burn your brains with this one. I don't know if I can defeat you, but I do seek to burn as many brains as possible with this one. And then the next one, forget about it. I know I'm going to burn a lot of brains. So read carefully and think. And actually maybe refer back to your notes from Thursday. Because we did talk about the SUN on Thursday. Let these guys think about it for a while. And, talk it over with your neighbor. I see a bunch of you guys pointing and talking. It's good. If you're sitting with somebody, you guys up in the front, you guys clicking okay? All right. Are you consulting with each other? Okay. Adrian, all right, you better supervise these guys. I don't know if they're getting with the program here. Let's see, look at this. A minute, they're still thinking. That's good. Think, talk with your neighbor, talk it over. Good. Good. Do you think your neighbor is correct, or do you think you're correct? Who's smart? Maybe I better not ask that. See how this is. This is an indicator that they're thinking. They don't have to. If I ask somebody, what's the value of pi? Nobody has to think. They just know 3.14. Most everybody. So you're just going to have a big spike. But if you're thinking about it, trying to make a decision, trying to reason your way through, looking back at your notes, there's going to be a spread like that. So, let's see. So we're going to show them that in a minute. All right, 20 seconds. I hear those notebook pages flipping. Good. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. Okay, now I'm going to show you go ahead and switch over to this. The correct answer is C, and and look at this. The correct answer is marked with the color green. Okay, switch back. So if you didn't vote for that, it's the V filter. Because the sun's peak wavelength is in the yellowish green, so that's definitely the V filter territory. And my wonderful students, that is why they use the V designation, V for visible light. The V filter is going to get a lot of Roy G. Biv, not all of it. None of these filters get all of Roy G. Biv. So, question? Yeah, it doesn't pick up all of visible, but I believe that's why they started using the V designation. I remember asking my astronomy professor the same thing, and that's what he told me. It doesn't pick up all of V, but we use it as an approximation of Roy G. Biv. So if you're looking for stars, so go ahead and make a note, everybody. If you're looking for stars, that are like the sun, look for ones that are brightest in the V, because that is where our star is brightest. So if you look at Alpha Centauri through the V filter, it's going to look a lot like our SUN. So now, I'm now going to incinerate many gray cells in many of you. It's been nice knowing you. You've been a lovely set of students, most of you, including you guys up here in the front row. But here's the brain burner of the century. Read carefully and think. Michaela, have you started working with Dr. Britt yet?
I think I started this week.
This week?
Yeah, I think so. I emailed them the day we responded. I went to the journal club meeting last night. They did a really interesting talk on Mars.
Yeah, I know, I missed it. I'm so clueless about all this other stuff. You're going to have to tell me when there's good stuff happening. Just 97. 1 minute. See how this one's stacking up. Thirty seconds. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let the students see this one. So there's a little bit of, I see some people high-fiving in the back. Okay, Smarty. Go ahead and switch back to laptop. Did you vote for this one? B? That's the right answer. Now, let me go through, for those of you that didn't vote for B, let me go through some of the concepts here on this list of options. And again, this will help you on exams, sort out possibles from impossibles. Now, one of the impossibles is C. And there weren't many students. We're not done. We still have more questions. Okay, good. Nothing is going to appear red through the B filter. The B filter is going to be kind of bluish, purplish. All right, so C is out, and by the same token, you're not going to see stuff appear blue in the V filter. If anything, it's going to be yellowish, greenish in that area. So now, bright and invisible, D. Definitely a hot blue star is going to have a lot in the B, but it's not necessarily going to be invisible in the V filter. Example, Earth. Earth has a lot of B and a lot of V. All right, so if you're a little bit hotter than Earth, what did I say, Earth? The sun. The sun has got mostly green is its peak wavelength, but it's got a lot of B. So for something a little bit hotter than the sun, you're going to have more B than V, but you're still going to have plenty of V. All right, so now nothing is going to option E. Nothing is going to appear invisible in the B filter. Okay? So if it's a hot blue star and the B filter is basically interrogating the blue pass band, are you bright or are you dim? If you're bright, how bright? So if you've got some money over in the blue pass band, it's never going to appear invisible in the B filter. All right? So now here's the bottom line, and this is actually the main topic for today. Measuring the brightness of a star, or anything really, any thermal object, any incandescent object, it can reveal a lot. It can tell us a whole lot about the star. Because the implicit message here is that for all the objects here, we had a known temperature for the last two questions anyways. Sun, 5,800 Kelvin. And you had it in your notes. Hot blue star, yeah, hot. So that means hotter than 5,800 Kelvin. All right? So now to get a handle on all this, I want to trot you through the magnitude system. Now I'm not going to spend a whole lot of time calculating in the magnitude system, but we do want to know what it is because the magnitude system is used for a numerical color rating system called color index. All right, so make a note of that. Color index is using the UBVRI filters and measuring a magnitude of a star through the filter. So the magnitude system. Now, the main thing that we want to emphasize with the magnitude system and all in luminosity is apparent versus intrinsic. Now, those are the two big vocabulary terms we're going to try to grapple today. Apparent brightness and intrinsic brightness. Now, if you think about, you're out in the middle of the mountains of Montana, and there's no street lights out there. There's no city lights out there. And if there's cloud cover, it is dark. It is really dark. You can't see your nose in front of your face. All right? So if you're out in the mountains of Montana on a cloudy night, as I have been many times, and somebody turns on a light bulb, one light bulb, like a flashlight, you don't automatically know how far away that person is unless you know that their flashlight is a little teeny, like the kind that you use on your keychain, or if it's a big torch, like the cops have, those big, the big aluminum jobs with, ultra high beam density. Right? So if you know what you got there, you can maybe tell how far away it is. By the same token, two different light bulbs of different intensities, if they're both at the same distance, you can know which light bulb is the small one and which one's the bright one. Okay? But if they're not at the same distance, a dim bulb, a little teeny bulb, like a 5-watt incandescent bulb, might appear, you might be able to read the newspaper with it. And like a totally bright 100-watt bulb, if it's half a mile away, you can't read jack with that. All right? So the distance and the apparent and intrinsic luminosity. So for light bulbs, the intrinsic luminosity is rated by the wattage rating. So a 60-watt light bulb, versus a 40-watt light bulb that you put in your refrigerator, versus a 100-watt light bulb that you use in the dining room to keep everything light and bright. Those are all intrinsic. That's a power rating. It's not a luminosity, but it's related to the luminosity. All right, so we're going to try to get that done. The distance is the key factor. So here's a pull quote from chapter 17, section 1. To measure the luminosities of stars, you have to first compensate for the dimming effects of distance in light. And to do that, you have to know how far away they are. And so that's one of the reasons that we like to know how far a star is by parallax. If we can get that, 278 parsecs or 482 parsecs or 1703 parsecs, then we can figure out, well, have I got a 60-watt bulb or have I got a 5-watt flashlight bulb? Now that's what we're trying to do. Right now, the way it works, and this is, go ahead and make a note, this is a figure 4 from chapter 5.1. So you guys, for exam 4, definitely you're going to have to be dipping backwards into chapter 5, right? For instance, this figure. The light intensity drops off by a factor of 1 over the distance squared, all right? Now this diagram here, we're going to use it to do a couple examples, and then you're going to do a calculation in just a minute with that. So what you do is you measure the apparent brightness here on our planet, and then you use the distance to calculate backwards, and with that you say, all right, I know how far away it is, I know how dim or bright it appears to be, and so I know that if I'm, if I were to walk up to, like 1 astronomical unit away, I'd know how bright it would be in an absolute sense. So you would be able to get the intrinsic luminosity of the source. Now let me repeat that for you. It's kind of a tricky argument. If you measure the apparent brightness, you're out in the middle of Montana, up in the mountains, and it's a cloudy night, so you don't see any northern lights, you don't see any stars, you don't see any moon, you don't see Jack, you don't even see your buddy standing 3 feet away from you. Right? Because it's so dark. There's no and so you don't have a campfire. So you're looking at a couple lights, and you don't, well, is that a flashlight bulb or is it a 60-watt light bulb? Okay? So you measure the apparent brightness, and then somehow like you use a radar gun and you figure out the distance. Okay? And then you can figure out the intrinsic luminosity. So that's like saying, if I know how bright it appears, and if I know how far away it is, I can distinguish between a flashlight bulb and a big 60-watt bulb. So write it down that way. So figuring out the intrinsic luminosity is like saying, I can distinguish between a small 5-watt flashlight bulb and a big household 60-watt light bulb. All right. Now, an astronomer is going to be able to rate it even more precisely than 5 or 60. All right. But yeah, that's how they can do that. All right. Now I'm going to blow up this diagram. All right. And let's add some notes to it. And I'm going to give you an example of how the light dims out. So this is figure from chapter 5. And let's say that here, 1 unit away, let's say that the solar constant, 1 unit away, is 360 watts per square meter. All right? Now we know that the solar constant for Earth is 1367, but for Mars it's like 800 or something like that, because we know it's going to dip down. Right, so this is an imaginary system, nice even number, 300. So mark down 1 unit away, 360 watts per square meter. All right, now, to figure out the wattage here at 2 units away, you use this formula. All right? So you take the original, 360 watts, and then you take the distance factor. That's 1 over the distance multiple, and you square it. So if it's twice as far away, all right, as the diagram shows, so this is 2 units out, that light's now spread over a lot more square meters, and so it's dimmed down by a factor of 1 over 2 to the 2nd power. And that's because it dims off as 1 over the distance squared. So if the distance doubles, the dim down factor, the dimming factor is 1 over 2 squared, 1/4. All right? Let me pause for questions. Yes.
So in the spectrum that we just went over, what is the B and the R stand for?
The filters.
Yeah.
I make questions about this diagram. But the B and the R stand for blue and red, just like the V stands for visible. All right? It's not really true blue, it's not true red, it's just kind of a... Okay, getting back to this diagram now. All right, questions about how to calculate this, because you're going to calculate this in a second. As soon as I pointed to you, you woke up. Yeah. Sit up. Okay, good. Sit up straight. Good. All right, because we're about to calculate something. What we're going to do now is calculate the brightness here. Okay. So hit your refresh key. Switch to numeric, please. Okay. Hit the refresh key. Now you guys down here in the front, hit the, no, not your phone, man. Hit the refresh key on your, good. All right. Because this, for those of you that are missing answers in your, who typed in a number? You don't even know what. For those of you that are missing answers in your clicking roundups, it's probably because you forgot to click the refresh key when I told you to. Anyways, I'm going to try to be ultra mother-in-law-like about it from here on out. All right, so go ahead and calculate the flux F at 3 times distance out here to the nearest whole number of watts per square meter. So out here, you have 360. What have you got out here at 3 times distance? All right, so if your calculation comes out to 202.87, type in 203 and hit the, and remember to hit the send key. All right, so now you can start typing in. What is this? I don't get that. I don't get anything other than this is. What is that? Oh, I see. Oh, you know what this is? That's 90 divided by, and so is this. And this is 360 divided by, which is to the second power. So I guess, I have no idea what that is. Look at that. That can't be right. That's a subtraction. Okay, 1 minute. This is good using the touch screen.
Yeah, it's really helpful.
So you're going to get this satellite up there. See, there's some. You're going to get that satellite up. When is this supposed to launch?
Spring 2018. Hopefully.
2010?
18.
2018? So a few months.
Yeah.
Where's it supposed to launch? At Kennedy?
Blue Origin. I'm not sure where they launch from.
Blue Origin, where's that?
That's the company that we're.
Yeah, yeah. That's Bezos, right?
I'm not sure.
I think it's Bezos. It's not Elon Musk. His thing is Falcon and all that stuff.
Yeah.
30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Yeah, most of you, the correct answer is 40. And, we're looking at the scoreboard up here. Go ahead and show them the scoreboard. Go ahead and swap over to that. I want you to look at the scoreboard here. Some of these, I don't really know how you figured them out, but now 270 is 360 minus 90. That's a subtraction. That's no good. It's a shrink down factor. That means you multiply. So the shrink down factor here for 3 times distance is 1 over 3 to the second, 1/9. So you just go 360 by 1/9, which is 40. I'll go down here a little bit. All right, now 22.5, that's 90 divided by 4. Now, you shouldn't be doing you shouldn't do any 4s at all in this. There's no dividing by 4 when you're at 3 times distance. You're dividing by 9. You're not, and now 120, that's 360 divided by 3. No, you don't divide by 3. You divide by 3 squared. You divide by 9. 90. That's the previous answer. And so that one's out. 18. Whoa, 270. That looks like a typo or something. 45. That's 90 divided by 2. Yeah. 180. 360 divided by 360 can't be the answer. It's definitely got to be dimmer. All right, switch back to regular. Let's continue with lecture. Anyways, you know what? I'll try to over the weekend. I'll give you some extra practice with this. Calculation practice and homework. Let's continue with talking about apparent and intrinsic brightness. So the luminosity falls off with distance as the factor 1 over d squared. So it doesn't have to be 2 times distance. It doesn't have to be 3 times distance. If it were 4 times distance, your shrink down factor would be 1/16. But if your distance factor was 2.5, then your shrink down factor would be 1 over 2.5 squared, whatever that is. That's 1 over 6.25, right? So whatever your distance elongation factor is, you square that, and then you divide by that, basically. It's 1 over that, the square of that. And we know that that's how it works in our solar system. The problem is watts per square meter, is nice. Neptune, it's about 1.51, and we've already talked about Mars. Yeah, 589 is what it is out there. So, It's kind of shaky trying to use watts or watts per square meter. But you can do it. I mean, we can, so what I'm trying to tell you is you're not going to get many watts or watts per square meter from a star. From Mars, maybe, Earth maybe, but if you're in the solar system, but not from outside. So what we have to do is take some alternate route. Now, the one that was developed by the ancient Greeks, Hipparchus and all those guys, or Aristarchus, Hipparchus, I guess is the guy's name, is to compare a star to some other star and then rate it numerically. All right, so what we do now, this is not exactly what the ancient Greeks did, but it's pretty similar. We now take our brightest, our 0 point. So this is like defining a temperature. Figure out where you want your 0 point, whether it's absolute 0 for Kelvin scale or freezing water for Celsius. For the magnitude scale, we take Vega to be our 0 point. And because Vega is a good bright star, and it's fairly close to what the ancient Greeks, the ancient Greeks, they oriented things to 1 through 6. And they said, okay, stars of magnitude 1 are the brightest. And stars of magnitude 2 are second brightest. They're dimmer. They're bright, but they're not. And then 6 magnitude is what they considered to be the dimmest star visible to somebody with good eagle eyes. All right, so they went 1 through 6. Now we go, and actually Sirius is a negative apparent magnitude. So in our modern system, we kind of have a similar rating system. In other words, the smaller the number, the brighter. And here's another rating system that you may have heard of if you've ever studied diamonds. In the world of diamonds, jewelry, they have a saying that the really brilliant, lovely diamond is a diamond of the first water, meaning the best. Okay? And everything else is, diamond of this, third water, I guess. But that's a saying, a numerical rating of the beauty of a diamond. And for stars, it's kind of counterintuitive. It's not like watts. The more watts, the brighter. In magnitude, the lower the magnitude number, the brighter. Vega's bright, it's a 0. Sirius, apparently, from Earth, the symbol is lowercase m, -1. It's the brightest of all the stars. But guess what? You could say Sirius is the brightest of all the stars, except for there's one star that's brighter. We've talked about it a few times. Remember which one is brighter than Sirius? Take a guess. Raise your hand, take a guess. Yeah. Alpha Centauri? No. Yeah. The sun. Sun is -27. Oh my goodness. So the magnitude system is good for stars and stuff, but solar system you don't really rate the. But actually, since the sun is a star, we calculate its apparent magnitude, and then we go with that. So let's do a table of some stars that we've talked about. And we'll just run the magnitude system. We'll set up a little table. Okay, so here are your objects. Sun, and we already know what that is. Full moon, Venus, Sirius, brightest of all the regular stars other than the sun. Vega, and Alpha Centauri. That was one of the guesses. It's pretty bright. Alpha Centauri A, Antares, red Antares, Polaris, the North Pole star, and the Andromeda Galaxy. And actually, that's the nucleus of the Andromeda Galaxy, which looks like as you guys know from the observatory, it looks like a smudge, kind of a blur in the sky. But to the naked eye, it looks like a point of light. Now, we know physically that the sun is brighter. That's at the top. And these other ones dim out, dim down. And Andromeda Galaxy, I'll never forget the time I sat on and spotted it for myself for the first time, naked eye, sitting on the dock of a beautiful lake up in Maine, clear dark night, summer, with a friend. And I showed her how to see it and stuff, and a lovely memory. But you can just, it's got to be a totally clear night. And you can see it. It's pretty dim. All right, so let's anchor Vega at 0. And this is the magnitude at Earth. So this is, or what we would call apparent magnitude. The symbol for it is little m, lowercase m. All right, and we have a different symbol. But this is an apparent luminosity. It's an apparent magnitude. It's not the true magnitude because we know that there's stuff, the sun, sun is negative 27. But if you were, if you could back up the sun, to like 50 AUs and Sirius to 50 AUs, Sirius would be, way brighter. Sirius A anyways. Right? So here are the rest of them. Full moon, minus 13. And Venus, minus 5. So Venus is pretty bright compared to Sirius. And if you were trying to, now I'll just go ahead and make a little footnote to history over to the side somewhere. These numbers can be converted into watts or watts per square meter. But you have to know the distance, and you have to use logarithms and stuff. All right? So we're not allowed to use logarithms in this class. So I can show you this little table, but not how to convert this into watts. But it can be done. All right, now down here, Alpha Centauri. So Alpha Centauri A is pretty bright. It's just a little bit dimmer, 0.01 instead of 0. A little bit dimmer than apparently from Earth. Now Alpha Centauri is pretty close. And Vega is a little more distant. Right, so if we were to, rate the intrinsic brightness of those two, Alpha Centauri would be dimmer, and we're going to do that in this second column, the magnitude, the absolute magnitude. Antares is 1, Polaris 1.97, and then you can look them all up. Andromeda Galaxy 3.44. So it's not the dimmest, but you have to be. It's tough to see. It's worth seeing. So now here's the problem that I, want to emphasize in this apparent magnitude scale. If we go with what the Greeks did, and then we apply it to the moon, Venus, anything in the solar system as seen from Earth, the sun, we got this problem where the full moon appears brighter than Sirius, but Sirius is a star. The moon doesn't have any light of its own. The moon would be, like magnitude infinity if it were far away from the sun. It doesn't have any light of its own, only what it reflects from the sun. So it appears brighter, but it isn't intrinsically brighter. So remember now, the word intrinsic means the rating on the light bulb, and it means the true physical luminosity or magnitude of the object that you're studying. So the way that we do away with this difficulty is we go to this column over here, the absolute magnitude rating system. Now, it's a magnitude, but it's the magnitude that you would report if you could back up Alpha Centauri to 10 parsecs. So that's so you have to be a good fair distance, So somebody decided 10 parsecs, I don't know. It wasn't Stephen Hawking, but some astronomer. All right, let's make the backup distance 10 parsecs, and then we'll figure out the magnitude from that distance. And then if everything's 10 parsecs away, we'll be able to know which one's the bright one and which one's a dim one. All right? So this is the column where you have to know the distance. Let me repeat that. To get this column, you have to know the distance by parallax or some other method. Now, to get the distance to a galaxy, we have other methods that we'll talk about next week maybe. All right, so let's take a look at this stuff. All right, here we go. Sun from Earth minus 27, but if we were 10 parsecs away from the sun, 4.83. That's nice. It's kind of dim, So if we were in a solar system or if we could copy the sun and move it 10 parsecs away, it would look like 4.83 on the magnitude scale. Full moon, zip zap, don't even think about it. Same thing with Venus, zip zap. Or put it like infinity, because it's, you're not going to see Jack. Sirius, 10 parsecs away, 1.42. All right. Let me ask you a question. Let me ask you an IQ test question. All right. Let's think about Sirius. Apparent magnitude is -1. Absolute magnitude, 10 parsecs distance, 1.42. Now, apparent magnitude is at its true distance. Absolute magnitude is the apparent magnitude if you were 10 parsecs distance, so that's an artificial distance. So let me ask you this. I want you to think. Is Sirius closer or further away than 10 parsecs? What do you think? It's closer. And why is that? Because at its true closer distance, it looks brighter than it would at 10 parsecs. Boy, that's a great sentence. Let me say it again. Sirius is closer than 10 parsecs because at its true distance, let me repeat. Let me back up. Sirius at its true distance is closer than 10 parsecs because it's brighter than it would be if it were 10 parsecs away. Say that 10 times fast. That's kind of a tongue twister. But that's how you can tell. So if you can get the distance, you can get an intrinsic luminosity. What? Let me ask you this. Okay, IQ test question. Look at the table. Which star, Vega or Sirius, so this is 50-50, which star is intrinsically brighter, Vega or Sirius? Which one's intrinsically brighter? Vega, because it's got an intrinsic magnitude, an absolute magnitude, a lower number. Sweet. Let's take a look at Alpha Centauri. Ding, 4.38. Pretty close to the sun. And that's why, Alpha Centauri, I always say it's very close to what the sun is. Same distance, 10 parsecs away. Their apparent, their brightness is pretty close. Antares, oh my goodness. Woo, doggies. Antares is pretty dim, isn't it? Minus 5.28, right? Right? No? No, man. Antares is ultra bright. -5? Yeah, you could have an absolute magnitude in the negatives. That's not a problem. Polaris, whoa. Polaris is pretty bright as well if you're 10 parsecs away. So you know what this tells us? Both Antares and Polaris are further than 10 parsecs away because they appear dimmer at their true distance. But at 10 parsecs, if we were 10 parsecs away, they'd be a lot brighter. Down in the negatives. And then at the Andromeda Galaxy, zip zap. So the apparent magnitude these guys are going to miss out on the key to exam 3. Apparent magnitude M ratings, if you measure it in the different filters, it's just going to tell you a lot of stuff. Distances, colors, everything. And this, my wonderful students, is known as a color luminosity diagram. So write down that word, color luminosity. Luminosity on the vertical scale. And this one is from University of Oregon. They have a nice astronomy site. And color, temperature, and look what they got up there. See that? The top numeric rating? That's B minus V. That's the color index. You rate the magnitude through the B filter, you rate the magnitude through the V filter, and you subtract them, and you plot that number. So you either do temperature, you do color index, or you do peak wavelength, or surface temperature. And when you do that, for as many stars as you can, you see a pattern. And this pattern here is called the main sequence. All the supergiant stars are up here, giant stars here, white dwarfs down here. Black holes are going to be way over here somewhere, way down in the luminosity. Here's another picture. The more usual name for it is the Hertzsprung-Russell diagram, or just the HR diagram. And this is figure 3 from chapter 18.4. And you see all different ways of expressing the color. And as you read from the homework, spectral class, OBAFGKM. You can use that as well. There's all, and this one is nice because it has a bunch of stars identified. So here's Sirius and Vega over here. All right. Here's the Sun and Alpha Centauri right over here. Here's Proxima Centauri. Here's some white dwarfs. Companion of Sirius right here. Yeah. Betelgeuse and Antares up here. Yeah. So here's Aldebaran. Here's a picture of these guys. Hertzsprung on the left, Russell on the right. And they figured this out about 100 years ago. About the time of the First World War. Now, my final comment for you today, and you guys can come up here in a second, is this. The most important thing on exam X was Kepler's third law and elliptical orbits. The most important thing on exam 3, isotope ratios, McKeegan. The most important thing for exam 4, not these two guys, but this. So your homework for Thursday, study 18.4, study as much as you can, and ultra study it. Try to, if you haven't already. Okay, you're dismissed. I'll see you on Thursday.